Hello, in this presentation, I would be solving a very practical problem. The problem is that you have to go to the station to catch a train at say 11 a.m. You left the station well on time, but unfortunately on the way something happened and now you are running late. This presentation has a prerequisite which is the video before it. The link should be somewhere at the description. The aim of that work was that if you need to catch your train at 11 a.m. at the station, what time should you leave your home and what route should you take in order to be assured that you will be able to catch the train with a good probability. So in general, it's not just you, but there would be a large number of vehicles which are somehow getting late and which are on a real time kind of task. So arriving after your train has left has no use. You have to go before the train will not wait for you. So people on such real time task, if they are running late, there's barely something that they can do, and therefore in order to cater to the needs of these people, we'll see how the transportation system can become cooperative and how can all the transportation entities and the other vehicles enable these vehicles to take some kind of priority. Now that is something that happens very natural in a human society. If you are in a queue and the person behind you is really getting late, I mean he really has to catch some train or he really has to go and reach some place, you might consider giving him priority, which is the right thing to do. So we'll see how such kind of things can happen in a transportation system where the vehicles not getting late give priority to the vehicles who are running behind time for such real-time kind of tasks. Now, even though we keep sufficient time well in advance, we plan for everything uncertain that may happen. There are various reasons why we may get late. You may actually have started late, so you might have forgotten your car keys. You may not be able to find them, or for some reason you might have started late. You might have been too optimistic in your traveling, so you said that the roads are never congested, while in general they might be a little congested. You might know that there is some engineering work going on, there's some construction going on in one of the route on the way, and you did not consider that, and hence you got late. And unfortunately, the vehicle a little ahead of you got with an accident, and therefore the traffic slowed down and it needed time to be cleared away. So you did not encounter, and we of course never encounter such non-recurrent trends. They may happen. So the problem is, once you are late, what can you do? And we look at it from a very broader perspective. We say that there are a few vehicles who are running late. Now, what can the other vehicles do? We think clearly. What can the different transportation entities do in order to make them from running behind time to running at a comfortable state or running on time? And the best way to think of it would be that what if any of these vehicles running late was an ambulance or an emergency vehicle, a fire brigade. One thing that we know for such vehicles, that they do not obey traffic lights. Normally all the vehicles at any intersection, each one of them crosses, and these vehicles can jump in traffic lights. In this implementation, I'll say that we'll not make them jump the traffic lights, but we'll make the traffic lights cooperative to these vehicles. And secondly, we know that the emergency vehicles or fire brigade, ambulance, whenever they move, the other people, they clear the lanes. They get aside, they leave the lanes so that these vehicles can travel at high speeds, and that's what we would be doing. That we'll seeing that how the lane changes can be made cooperative towards these vehicles which are running behind time. Now, this part of the problem we've already seen in the previous video, where we learned some kind of traffic information which consisted of the average speed and the variations of the different vehicles, and we used it to solve the very nice problem that suppose we had our train at 11 a.m. what time do we reach leave our home say at 10 a.m. and what route do we take? So it might be a number of roads and all these as intersections. So this is a problem that we've already solved. Now suppose you left your home at 10 a.m. as your system guided you. Good enough. You are at this intersection out here. So this is an intersection like this, and you are supposed to travel here. You reach this intersection as say 10:35 a.m. while your actual planning said that you should be reaching this intersection by 10:30 a.m. So now you are running 5 minutes behind. You should have reached it by 10:30 a.m. Now you actually read by 10:35 a.m. So now how can the traffic lights be made cooperative towards you or other vehicles like you, and how can the lane changes be made cooperative towards you or other vehicles like you which are running behind time? Now, more broadly, we said there was a route where there was one intersection here. You should have ideally be reaching this by 10:30 a.m. So this 10:30 a.m. is actually my expected time. This is the time by which I should be reaching my this intersection. If I reach this intersection later, so say at 10:40 a.m. Now I need to consider, I need to be worried about, I really need to be worried about. So 10:40 is the time after which the panic really starts to take away. 10:31, 10:32, I'm almost on time, it won't matter, but something like 10:40, panic will start to take away. Human drivers normally tend to increase the speed, which is obviously not legally legal and neither it's advisable. So I'll become a lot concerned. But let's say I had to reach my destination by 11 a.m. but by 10 say 48 a.m. I am at this intersection. Now I know my general expectation is that it will take 30 minutes to reach from here to here. 10:48 I am here. In any case, even if I drive very fast, even if I show a little bit of aggression, in 12 minutes I'm not reaching this station. And because 12 minutes I'm not reaching the station, there's no use, the train would have already left. So I have something known as the cancel time. Remember, reaching late in my problem had no use, the train would have already left, or it's a real time task. Going after the allocated time is worthless. Now humans generally do not do that. They have nothing called as cancel time. Even if they know that even if miracle happens they are not reaching by 11 a.m. they'll still go in order to just ensure themselves that we tried everything. But for here, having more practical considerations, this has been taken into account, a cancel time, wherein this journey in order to reach at 11 a.m. is abandoned, and obviously the human may have some other plans. He may go home or he may go to the station to find a better train or whatever. So this journey, as far as it is concerned, that is abandoned. So I draw the same thing again. I say that there was a route I had to reach at 11 a.m. here. I reached at 10 a.m. here, and there was an intersection out here. I reached this in my expected travel time to reach this was 10:30. After 10:40, panic starts to happen, and after 10:48, I should easily give up. So if I've reached at say 10:15, I have 15 minutes time, so I'm running way before time. I can even slow down, or normally I'll not slow down, I'll still drive, but I'm not at all concerned. I'm running way before time, so I'm in a very comfortable state. At 10:35, I'll start to get a little concerned. I still know that there's nothing to be too worried about, but I'll start to get a little concerned, which is known as my late state. It might be visible in the general way I drive, but 10:45, of course, I'm a lot concerned. I'm running way behind. I'm running behind 15 minutes. My late time was 10:40, so I'll be very concerned. I'll start to panic, and of course, 10:55, I'll give up. I'll say there's no use to drive. So if this is my time axis, which shows the different times of the day, and these are the three times that I denoted. all I have done is that I have stated a vehicle can be in any of these states. These are discrete states. A vehicle can be any one of these states at any general point of time. It can be higher up in a state where it is less comfortable, or it is more comfortable, or where it is less concerned or it is more concerned, or it may be low upon a state, but it will be at any one of these four states. And if we map those four states into a real transportation system where there's a road network, all these are various roads. So I see most of the vehicles, of course, they are on leisure making, meeting friends, and all such kind of things, where there may either be no deadline, there may either be no time, or time may be a very soft constraint, so it's okay even if you are late. Very few vehicles would have given up. Basically, it rarely happens. If 100 vehicles go, then not even one vehicle would be in a state of giving up. We take good margin well on time, and most of the vehicles which actually need to go on a real time task like catching a train or something, they would be well comfortable on time. They would have taken enough of slack time. The problem is these vehicles which are running late, and there are very few of them, as it may be apparent. So how can these vehicles cooperate towards these vehicles? And naturally they would not mind cooperating, because these vehicles getting late, they are very few in number. That is my research question here. How can these vehicles which are very large in number cooperate with these vehicles which are very small in number? Now, the algorithm as it goes, the general planning algorithm as it goes, is similar, or it's basically exactly the same for computing the start time and a route. So my part one of the problem was that I needed to, in order to reach station at 11 a.m., it was at what time do I leave the home. So this is the home. So at 10 a.m. and what route do I take? My algorithm is same. In fact, it's the same problem. So it's exactly the same algorithm as was presented in the previous video. So I will not be repeating that. The only problem is there in that particular problem, for every intersection, what we were doing, we were calculating in one time, say expected time. That was one time that we were calculating. So it said that at 10:30 you should reach this, leave this intersection, in order to hope that you reach by 11. By 10:45 you should be leaving this intersection. By 10:18 you should be leaving this intersection, in order to hope this on time. That was the only thing that we were calculating. The only modification made to the algorithm for computing the start time and the route is that now we will be calculating 3 times the expected times, the late time, as well as the cancel time. So for every intersection, I'll be calculating 3 times, and that would be quite apparent from the previous figure, where we said that the expected time here was 10:30, the late time was 10:40, and the cancel time was 10:45. So these 3 times are calculated at our graph search for computing the source, for computing the route and the start time. A very simple way of calculating these 3 times would be that the expected time I was anyways calculating in the algorithm of the previous video. So this 10:30 I was easily calculating. So let me just say that my late time will always be 10:30 plus 10 minutes. So it becomes 10:40, and my cancel time will be my expected time plus 15 minutes. So that becomes 10:45. So this 10 minutes and this 15 minutes rule I can apply, which is a very bad thing to do, because near the goal, or if this was my source and this was my route and this was my goal, near the goal, these 3 times would be very close to each other, because very less uncertainty can happen over here, and very far from the goal, these 3 times would be much different. So let's say that would be 10:05, 10:25, and something like 10:35 out over here. because the distance to the goal is larger, and distance to the goal is larger, so the uncertainties are large. If the uncertainties are large, my different times are differently tuned. Now, away from the goal, when there are such large time differences, of course, the other thing that I can also say is that I can simply imbibe this as heuristic, that nearer to the goal, the time difference will be 10 and 15, and farther away it will be like this, it will be much larger. So it solves this problem. But the other problem that comes up in that when my time differences are so large, they vary by 20 and 25 minutes, my traffic trends of 10:05 will not be the same as my traffic trends of 10:25. Congestion of 10:05 may have cleared by 10:25, or congestion of 10 which happens at 10:25 might not be visible at 10:05. So because my traffic trends are different, each one of these times it's separately calculated in the graph search algorithm, or for every intersection I will use the same strategy as used in calculating the expected time to calculate these two times as well. Or the fact that for every intersection I will be maintaining these three times separately rather than having just a rule that correlates them. And that's obviously because the traffic trends at these three times may be very different. And a quick recap of how we said that we would be calculating the expected time. We said that this is the distribution which covers the number of vehicles and the observed speed. My time was simply my distance of a road like this divided by the speed. My speed was stochastic in nature. I had to convert it into a discrete value. So I said I'll be choosing at from this discrete intervals. I said that this is my average, assuming an average would be bad, so I moved it just a little left of the average, which became my expected travel speed. So this was the speed selected in calculating the expected travel time. Exactly the same thing I will be doing here, except for selecting one speed out here, which was done in the previous case. Except for this selecting only this one speed out here, I'll be selecting three speeds. So this is 1, this is 2, and this is 3. One will be needed to calculate the expected time as in the previous video. The second would be needed to calculate the average, the late time in a similar fashion, and the third would be needed to calculate the late time. So the same strategy is being used. In fact, the slide is being repeated. This is a magnified view of this things got congested, so I put it up in a cleaner slide out over here. So there is a same distribution which covers like this. This is my average speed. So this is my learned information that how much does an average vehicle take from reaching this intersection to the next what average speed does my vehicles show up at this road. I said that my average speed minus alpha time deviation would be what is my expected time as in the previous video, where I kept in a risk region of alpha times deviation, which denoted how much lag time do I keep. So let's say by average speed, an average vehicle should be here by 10:43 a.m. By the average time, an average vehicle leaving at 10:43 would just be able to reach this station at 11 a.m. What my average time would be, it will be say 10:30, because I have kept in this time minus a window of alpha times deviation. So this is what will be my expected time. I will keep a narrower region which is beta. I'll keep in a narrower risk time region, and I will calculate my late time. So let's say that is 10:40. Of of course, this is the time scale and this is the speed scale. So I should not really be comparing the speed scale to the time scale, but intuitively we know that how do the travel speeds link to travel time, and how do they link to this time or the time of latest arrival. And I will keep in a positive region, so my late time will always be more than my average, my average speed, my average vehicle expects, so that will be 1048 out over here. So that will be my cancel time, or the time when I cancel. So I'm leaving a broader region here, I'm leaving this risk region here for calculating my expected time, a narrow risk region for calculating my late time, and a positive risk region. That means I'm expecting my vehicle to travel greater than the average speed, which is what we would consider for cancel time, wherein we completely abandon the vehicle. A region of gamma times deviation for calculating my my cancel time. And that's what we've already seen, that a high alpha meant a more risk region, or keeping more resistance to risk, or an earlier start time, which enabled me to increase my probability of reaching on time. That is when the vehicle decides at what time to start, or decide the time of leaving at 10 a.m. Once it's there out at the road, or once it's there at some intersection like this, if I keep my alpha and beta, or these two regions, to be very high, then very early I'll become very conscious that, oh my god, I'm getting late, oh my god, I'm getting late. If I very early get conscious, such kind of conscious, then I will ask the other vehicles to give me priority very early, which is good for me and that is bad for the others. So basically, cooperation is a good tool. It must be asked only when needed. If you always ask it, it's not a good thing to do. It's socially not a good thing to do. And similarly here, high alpha means asking too much cooperation too early, very early in your journey, become conscious, it's bad. High gamma would mean that I'll give up too early. So that would mean that I'm at 10:45 here from my, or 10:43 I am here from my previous experience, that I know that an average speed might just reach at 11 a.m. but I'll still say that, oh my god, let's leave this journey, or let's say 10:45 here, I'll say that let's leave our journey, while still it could have been possible. Vehicles would have moved away, things would have cooperated, but I'll say that no way that I'm reaching, I'll give up too early. And of course, if I give up too late, then I'll be unnecessarily pushing the other vehicles. I'll be unnecessarily asking for their cooperation, even though I know that practically I cannot reach now, which is bad for the other vehicles. So whenever I said that there are too many, so there are four kind of states associated to three kinds of times. Of course, the strategies went different. The strategies were very different. But what I need to do is that I'll be mapping in those states to some numeric values that will denote priority. So a vehicle higher up in a in a state meant it's getting very late and it will ask for more priority, or its priority would be high. So a very late vehicle is preferable to a late vehicle, and hence its priority, or this numeric number here, would be high. And a late vehicle is more preferable, or it has higher priority than a comfortable vehicle. And similarly, we said that the comfortable states were in stages. So if it was 10:30, if it was 10:15 here and 10:30 here, a vehicle closer to 10:30 has got higher priority than the other one. And similarly in late, where this will become 10:30 and 10:40, a 10:40 vehicle has a higher priority to the 10:35 vehicle, and the 10:38 vehicle has a higher priority to 10:36 vehicle. So it'll have a higher number out here. So I basically mapped on those states to a numeric cost, which is very simple to do. The interesting point here is that even if a vehicle was running comfortable, even if a vehicle was running way on time, so at 10:30 I had to be on this intersection, and I reached it by 10:25, I'll still be asking for a little bit of cooperation from the other vehicles or from the transportation system. Now, why did we do that? Suppose you had to reach your station at 11 a.m. out here. 10:25 you left here, 10:45 you left here, but there's a large traffic jam out over here, and you reach by say 11:02 a.m. because of this traffic jam that happened very late. Now, because this traffic jam is happening just before the station, there's nothing you can do about it. Even if the other vehicles cooperate, it's too late. The time lost is gone. You are already next to the station with very little time to spare, and hence there's nothing you can do. And as it can be seen, you were late only by 2 minutes, but late means late. The train is gone. So I've given a small cost, so even if a vehicle is coming late, is running late, it'll precautionary ask for cooperation. It'll not affect the vehicles getting more late, as they would obviously have higher priorities. But if the other general vehicles, it can give it priority, it'll give. So that's what will happen. That if at 10:25 I'm here, I'll still push the other vehicles to make sure that I do not reach at 11:45 here, which is my expected time. I reach at somewhere around 11:40, so I have an extra 5 minutes. Whatever might happen right at the end, or likewise. So after I have computed my start time here, I have computed my route over here to reach at 11 a.m. say here, and for every intersection I have got my expected time, I have got my late time, and I have got my cancel time. I'm done with the first part of the problem. The second part of the problem is cooperative traffic lights, and the third part of the problem is of course cooperative lane changes. So I have got an intersection like this where there's a pack of vehicles out over here. I will add up the total lateness of all the vehicles. So let's say some vehicle was very late, I have a corresponding priority to it, I have a corresponding cost to it. Some vehicle was going in for comfortable when it has a miniature contribution of epsilon. I had a vehicle that was very late, I'll have a greater contribution from it. I added it up for all these three vehicles, for all these four directions, 1, 2, 3 and 4. Whichever side has the highest lateness, whichever side out of these four has the highest lateness will be allowed to move, or the traffic lights would change. So let's say this side has the highest lateness and this is allowed to move. The traffic light for these vehicles get up green, and after the threshold time pass or the threshold number of vehicles pass, this decision is made again. So I'm basically deciding on the basis of the total lateness, which is my primary criterion. My secondary criterion, if two sides have same total lateness, or let's say no vehicles are in these pack of vehicles was actually getting late, so they were all vehicles which are not going on such real time of tasks. So I again have four packs. Now here of course the intention is the thing is that the assumption is that all vehicles can be traced. Their entry points at traffic is recorded, their exits at the traffic lights can be recorded, and hence after, of course, a magical thing happens that after all the vehicles at a particular site they leave, my traffic light will not wait for the threshold amount of time, as in the present scenario where there are only two vehicles at one side. The traffic light turns green for 35 seconds and it basically waits for the excessive 20 seconds where there are no vehicles. So here what would happen, that as soon as the vehicle from one side clear, a traffic light change will happen, and it will happen for the earliest emergence, which is making this system towards a first come first serve basis system. Now we know that in a queue, the earlier one comes in, the earlier one gets served, or a first come first serve system is followed. So similar is the scenario here. The earlier a vehicle comes, it should have the right, it should have the demand to go out of the first. A vehicle which comes first into the traffic signal, it goes out for first from the traffic signal. And of course, the traffic light would change for a threshold number of time for a threshold number of vehicles. Considering that too many traffic light changes have gotten late, there's little time between traffic light changes, so we need to minimize the loss due to those lateral times as well. So anytime the earliest vehicle it is allowed to travel and the green light will happen for a threshold amount of time. So my primary criteria is total lateness and my secondary criterion is earliest emergence, and I've got a nice little graphic out here. First this vehicle came, then this vehicle came, then this vehicle came into crossing, then this vehicle came into the crossing, and so on. Now I can see the total lateness here is because of one vehicle here, but here this vehicle is getting very late. These two vehicles were just late, this is getting very late. So the traffic light would turn green for this side, or these two vehicles would be allowed to go wherever they are going, either of the places. Once these two vehicles leave, this becomes my first vehicle that entered the traffic scenario, this becomes the second, the third, and the fourth. Now these two vehicles are getting late by an equal amount. These two vehicles are on a non-real time job, they do not mind anything. So there's a tie, and because there's a tie, because this vehicle came earlier into the traffic crossing, it should have the right to leave the traffic crossing earlier, which means the traffic light would change to allow this vehicle to go wherever it's going, and after that these vehicles can go. So that was the second part of my problem, or the cooperative traffic light. The third part of my problem is cooperative lane changes. Now I'll first be presenting the standard criterion of lane changes, and then how do we modify the standard criterion, unlike the previous slide where I first told how to handle vehicle lateness, and then I said what's the standard criterion. So at any time, suppose there are three lanes like this, you are here, there are some vehicles out here. If this vehicle is traveling faster than you, then you need not care for, you can simply follow this vehicle, you're already traveling at a very high speed, that's okay. But if not, you try to go to a lane which has got the maximum time to collision, and time to collision can be infinite, so infinite is the best. And time to collision basically says that if this vehicle is very far away, then this lane change is preferable because you will get this extra distance to travel with high speed. And if this vehicle is traveling faster, then this lane change is preferable, your speed would be higher. So it combines both the distance and the speed factor into one single metric. So anytime I'll see in what are the choices of lane possible, and I'll select the lane with the highest time to collision. The only exception is that in a spatially occupied scenario, let's say like this, where the vehicles have diverse speeds, the lane change makes sense only when the speeds are different in a non very congested kind of road. So let's say this is driving at 30 miles per hour, you're driving at 35 miles per hour. You may of course change the lane because time to collision would be infinite here. But after reaching here, you might want to dip back. Time to collision again is infinite in both these lanes. You are anyways traveling at the highest possible speed of 35 miles per hour. You would like to move back. And why would you like to move back? Because it is possible that there was a vehicle traveling at 40 miles per hour. Now it will make its job very easier, where it will first overtake this vehicle with 30 miles per hour like this, and then it will overtake you at 35 miles per hour like this. After which, if there is no vehicle here, it might always dip back. So that's the overtaking based lane changes, where if you are traveling with the highest speed or near highest speed, you're always driving at the leftmost lane in order to make overtake of the other vehicles possible. And this is how we change it. We'd say that if a vehicle is getting late, behind, you should always change in a lane. So basically consider this as the emergency vehicle, as a fire brigade or something. This I will have to change the lane in order to make this fire brigade or this something. But the worst thing would be that if this was not a fire brigade, say it was a minister's car, which are again high priority vehicle, and there was a fire brigade here. In order to give this vehicle priority, I changed the lane. I came in out here. Now fire brigade has a priority. So if there are two vehicles, I cannot change a lane and come in front of a vehicle which is getting more late. So out in this scenario, I cannot come in front of the fire brigade, or I cannot come in front of a vehicle which is coming more late. Instead, if there was a lane like this, I would have gone here. If there was nothing out here, or there were vehicles out here which were not getting late. So this is the basic essence of how lane change happens. I will always change lane if there's a high priority vehicle behind, except for when I'm likely to get in front of a vehicle which is getting more late. Now from an algorithm perspective, it is very simple to see how all this is happening. If all these three vehicles are autonomous in nature, they can say, this vehicle can say that I have a cost of 35, I have got a cost of my lateness cost of 45. This vehicle can say I have a lateness cost of 0, I don't mind getting late, I'm not on a real-time task. But these 35, 45 and 0, these numbers would not be there if a human is driving the vehicle. So if this vehicle is being driven by a human, or they are not autonomous, or they cannot collaborate with each other, then this person does not know how much this is getting late and how much this is getting late. It just sees two vehicles driving behind. It does not know how much are these two vehicles getting late. And so therefore we use again the same analogy of the emergency vehicle, where this may flash in some light and this may flash in some light. They may not be siren. It's very annoying. And that may not be that emergency kind of light where you have to immediately get aside. It may be a more softer light, and you may use colors to denote which state you are in. As I did in the previous slides, there was red and there was green and there was pink. So we can make in some codes in order to make this human driver aware how much is this vehicle getting late and how much is this vehicle getting late. And again, these vehicles getting late will be very few in my entire transportation infrastructure. And this is the example which basically shows which lane change and how to lane change. The first scenario, a high priority vehicle behind, I have to make a lane change no matter what be the time to collision, no matter what be the best lane. And second scenario, even if the time to collision is positive here and it's an infinite here, I cannot make a lane change because there's an emergency vehicle out here. The third scenario, I have a mandatory lane change because of the fact that this vehicle was getting more late and this vehicle was getting less late. If I have to choose between a vehicle getting more late and less late, even if my time to collision is infinite here and it's not infinite here, I have a mandatory lane change. A more late vehicle has a priority. And if I switch these two, I cannot make lane change because this is the minister vehicle ambulance case. In order to give minister's vehicle some priority, I'll come in front of ambulance, not suggested. So a disallowed lane change. And with this, we come to the end of the algorithm. These are similar results that you would expect from the previous video. If I increase my alpha, what happens that the vehicle starts, the distribution starts shifting rightward. That means lesser number of vehicles get late. If lesser number of vehicles get late, but the time increases, or my waiting time, it increases. So this is with cooperation for some values of alpha. This is again for some values of alpha. This should be alpha out over here. So again, for the other values of alpha, this was when I use cooperative intelligent transportation system. If I do not use cooperative intelligent transportation system, in general, what you'll obviously observe, more vehicles will get late. There is no cooperation. Once they get late, they just get late. And again, similar trends are seen. The distributions would be a little more leftward out here. These are for some values of alpha without cooperative, without any kind of cooperation, and these are for the other values of alpha without cooperation. And if I see that how many percentage of vehicles turn late for different values of alpha, I nicely see that with cooperation, as expected, there were lesser percentage of vehicles getting late. And if I see that the vehicles that were getting how much earlier was an early was a vehicle arriving, I see basically very little change. This is of course a little leftward, and this is a little rightward in general, because the scale of this axis is so big, it's not apparent. So the vehicles reach earlier and earlier if I make transportation system cooperative in nature, which is again expected. And in order to better analyze this, I took the percentage, how much is my cooperative system better from my non-cooperative ones, or how much less lateness does it produce, how much less percentage lateness does my cooperative produce as compared to my non-cooperative one, and can be easily seen how these two systems die off with alpha. A very high value of alpha, they both basically make the vehicles reach more or less on time. And this is basically that if I had to reach on 11 a.m., some vehicles reached at 11:05, some vehicles reach at 11:08. If I add up total cost, then I see the total lateness is much less as compared to the one without cooperation. So earlier I saw, when I plotted the actual presentation, it looked that the gap between the two systems is very less. It seemed that cooperation is not doing very much, but here it gets amplified. Here I can exactly see that with cooperation, they are of course vehicles getting late, but they are getting late by a narrower margin. So a little bit of offset would enhance the performance radically. The vehicles are getting less late in total. All the vehicles which are actually getting late, they are actually getting, with cooperation, they are actually getting late by a very minor amount as compared to without cooperation. And that will be all for the presentation. Thank you.